we have the speaker who is going to be, take over the mic and also introduce interesting subjects about data visualization and communications. And especially, this is actually a very important skills for many of the, I would say, junior, middle career, and even senior fellows, how to actually, make the research results having real impacts into real world industry, society. And then I think Engin definitely happy to have you here to share your insights and also give this talk. So now let's pass the mic to you.
Okay, thanks a lot for the introduction. Maybe I will share my slides.
Yeah, go ahead.
Okay, so can you see it?
Yes, yeah, we can see it now. Yes.
Okay, perfect. So yes, so I will, like I said, I will talk about data visualization. So the title is Data Visualization and Communication of Results, but this is a little bit different perspective. So I will come from a data engineering perspective.
Yeah.
Because at the end of the day, you need to some pre-processing as well. So this is, I think, also important in addition to the data visualization aspect. Of course, it will be also one part of it. So let me quickly, because we don't have much time, so it's 45 minutes. So I will try to. So this is more or less, I think, a little bit longer usually, but I will try to squeeze it to 45 minutes. So I will first, I don't know if anybody doesn't know data engineering, but I will so to give an introduction of data engineering. Then I will give you these 6 frameworks: data connection, data ingestion, data analysis, processing, data storage, data monitoring and visualization, and data orchestration and management framework. So these are 6 main frameworks that I will describe in today's talk. Of course, as you can see, data visualization is one aspect, but to come to data visualization, you need to also know these different frameworks, how you can stitch them together to make the data more visualizable, analyzable for your needs. So this is more or less the outline. So during the talk, feel free to interrupt. If you have any questions, I will be happy to answer.
Yeah, maybe just one quick
yeah, sure.
Notice that, so we are recording the sessions. So I assume that you're okay with this because later this is for the project. Maybe some of the contents might be put online. Is that okay for you?
Yes, I think it's okay.
Okay, thank you.
Sure.
Yeah.
So just to start, so I am working as a senior researcher at Services Network Research Unit at CTTC, which is based in Barcelona, Spain. So I have previously around more than 7 years of experience in an R&D department of Avayan Türk Telekom, a mobile operator in Turkey, involved in previously data projects on networking and machine learning approaches, and also lectured some networking courses in Özyeğin University in Istanbul, Turkey. So my research areas are on data engineering, networks, communication, machine learning, and also things related to network security. So let's start with the introduction. So what I want to say is that the companies actually that you see in the community are when you look at the most valued companies, you will see Apple, Microsoft, Alphabet. So these are actually, you can also say that these companies get their benefits from advancements in the networking. For example, Apple has become the most valuable company after it has switched from computing to communication with the introduction of iPhone in 2007. But when we look at the value chain of the networking and how it impacts the large communities, we can see networking is actually in the middle. So it's not like high valued or reaching large communities like application services, but it is something that is bridging between the device manufacturing to the applications and services. So this is more or less what we can think is networking is something like a backbone. So when we look at this picture, we see nice room with a very clean site. But when we go underneath, we see this plumbing, which is actually the infrastructure that is supporting this nice picture. So we can think of this networking as backbone or plumbing of the computing. So almost all areas of computing that we are thinking are networking based, blockchains, smart cities, Internet of Things, cloud computing. So all the enhancements are relying on networking. For example, if there is some failure in the system, like this is, for example, radar failure, it is becoming a news in the top headlines, and it's important occasion that happens. So the AI is also something that is already discussed. Everybody is discussing now. So people are thinking you have an AI as a black box and you put some data, you get some value, but it's not like this. There are many things that needs to be considered. So for the data, you need to consider sourcing, synthesis, selection of the data. For AI, it is you need to also explore, clean, normalize, do some feature engineering. Also, you need to do modeling, training, evaluation. So this is actually the things that you need to consider in the data science part. And also to get the value, you need to operationalize it, register, deploy, monitor. So these are actually also you need to handle it. On top of it, you also have constraints to give this kind of AI services, legal, ethical, security constraints. All these things needs to be considered when you are taking some value from some data. So when we look at the ecosystem, data AI is very big. This picture comes from 2019. Of course, now it's quite larger than this. But it is, as you can see, there are different companies, services provided by different layers, infrastructure, application, analytics domain. So what's data engineering, right? So data engineering, we can also think of it like plumbing. So it is can think of backbone of the data science, because all the AI-enabled applications and services actually relies on data science, but data science is actually also relying on enhancements in the data engineering. So this is, I think, will be more clear at the end of this presentation, that all the things that we see in terms of data space are thanks to the enhancements in the data engineering space that enables this. So why do we need to study data engineering, right? So we have large data sets now, low cost of storage. We have powerful multi-core processors. The distributed computing is low latency. So we can have virtualization, partitioning, aggregation, isolating of resources. Of course, now we have affordable and increased computing resources, GPUs, cloud sources. We have better understanding of test distribution and compute architecture like Hadoop and Spark. Now analytic techniques are larger. We have machine learning, AI, and also managed data platforms provided by big companies like Amazon, Google. And also we rely on extensively on open source software like Spark, Flink, Hadoop that are already in the production. And there is a large community that is supporting these data science applications and engineering. So these are all actually some of the, let's say, ways that now data engineering is getting more important than ever due to these enhancements that we observe in the community. So what is the data engineering ecosystem, right? So it's not only based on one part, but I think this is the generic slide that I want to show you. This is the most important slide that I want to mention. So it is actually including 6 frameworks, 6 modules. So to be able to, let's say, do something on the data, you need to first connect to a data source, whether it's an API or a data flow or some file that is stored at some place. Then you need to be able to take this data and ingest it, so you can put it into some message queues or buffer zones, so that the other modules can get this data from these message queues or buffers. And then this is the data analytics part. You can have, this is the more or less the AI machine learning. You can have stream batch analytics in this kind of modules. You can also have data storage part modules, which are these databases, NoSQL, NewSQL, SQL databases. And then this part is related to data visualization. So you, after you somehow get this data, analyze it, you need to visualize it in an appropriate manner. And last but not least, you need to have a data management and orchestration framework, because as you may guess, there are many pipelines built between these frameworks, and you need to be able to know which pipelines are connected to each other to get some results. So I think this is, I hope this is clear, because this is the slide that I will go one by one to each part framework, and I will give you open source tools that you can use in each framework to be able to do this kind of objectives. So let's start with data connection frameworks. So this is the place where you connect to data, right? So this is where it is serving as a trigger. So the data is stored either in a cloud or a local file, and you need to be able to connect to this data source. So this is very important, because you need to be able to enrich your data with third-party resources. It can be either streaming, it can be some storage database, clickstream logs. So you need to know how you can connect to this data. So of course you can devise your own frameworks, but it's better to use what is already existing in the community. So these are actually some of the lists that shows the different data connection frameworks, like REST APIs, gateways, Kafka Connect, Apache Flume, Scoop. So these are all actually some of the exhaustive list that I showed here. For example, I will in the next slide, I will describe Apache Flume. But you can use any of these tools to be able to connect to your data source and get the data to any place that you like, okay? So you don't need to do it from scratch, but you can use these kind of tools to be able to get this information. So for example, Flume is used to import data into a data cluster. For example, any log file that you observe from a web server. So you can keep track of these log files and put it into some database like HBase or HDFS, so that any changes in the log files are immediately put by Flume into the database. For this, you need to configure the source and the sink information. So you can, I mean, this is basically a configuration of the file that you point out the file that you want to update, and it's automatically, let's say, following this log file in your system. And if there is some changes in the log file, it's automatically putting into the sink, which can be any data store that you can pick. For example, these Flume agents can be configured to get different data sources, web servers, logs, and they can put it into another message buffer, for example, Kafka. So each agent can follow changes in the different data sources and put them into some message bus in the next step. So what kind of data we have? We have structured data like MySQL, or unstructured data. It can be, doesn't have a formal data model like XML files, but most of the data we have is unstructured, which doesn't have a predefined meta model. It's text files, video files, audio files we have on the internet. they're all unstructured data. So this picture is showing the telecom perspective. So from a telecommunication operator, you can also have these different kinds of data sets, semi-structured data, geospatial data, structured data, unstructured data. So these are all data sets. You need to know how to connect to these data sets and put it into your cluster to get some information out of it and also extract some knowledge from all these kind of data sets that you can extract in the ecosystem. So just to say, IT systems, information, network systems data, so these are all examples from an operator perspective, or some application data that you have some products and services. So these are all sources of data. So at some point you need to know what kind of data you are dealing with and how to take this data source and put it into the appropriate place. So this is the job of the data engineering pipeline, to make sure that the pipeline is ensured to get the data that you want from the system. So this was the first part. The second part is related to data ingestion, which is now we are here. So after data connect, we need to put it into some temporary place so that other subscribers can subscribe to it and get this data. So this is like an intermediary data hub that, for example, different subscribers can connect and then they can get this data. So this is used to enable replication and partitioning of the data across the nodes. So that, for example, if you connect to data and this data, maybe you don't want this data to be lost, you put it into some temporary place, and then you get some, let's say, benefit that you can maybe analyze this data later on for all your systems. For example, these are some of the tools like Kafka, Spark Streaming, or Scoop, that provides you this data ingestion capability, so you can subscribe to a data set and then, or topic in the Kafka's case, and then this data is stored in a temporary message bus so that other consumers can get this data. For example, this is how showing Apache Kafka works. You set this distributed publish subscribe messaging system. So you have some data producers, you have some broker where you keep your data in a cluster. This can be scaled very nicely. So the consumers, like you can have different consumers, they can subscribe to this topic that producer puts to it, and then consumer can get this data from the broker. So this is enabling hundreds of megabytes of reads and writes at the same time. So thousands of clients can subscribe to this data to get this information that is put by the producer. So this is an example just showing that you can produce log files, some application, some publish some data under a certain topic. And then this topic can be consumed by different consumers like data lake or API to give some application alerts in case something happens in the data that you are subscribed, topic that you are subscribed to. The good thing is that this, like we said, this can be parallelized and you can have hundreds of thousands of clients and can reach to different terabytes of data. And so there are different semantics that you can use. For example, to producer, there is at most one semantic. In this case, you produces data, but consumer is pulling the data once. So it can either get it or not. So there is no duplicate, but there is a chance that the data is going to be possibly missed with this at most once frame semantic. If you have at least one semantic processing guarantee, so the consumer is going to pull the message one or multiple times, and it's going to be processed every time. Reception is guaranteed, but there will be multiple duplicates that you can receive, but the data is not is not missed. So everything is guaranteed to be received at least once, but the disadvantage is that you can get multiple of messages. For example, if you are posting some pictures in some platform, it can happen that the consumer can get the multiple copies of this picture in this kind of at least once semantic. But in the exactly once semantic, the message is pulled one or multiple times, but the processing is done once. So reception is guaranteed. There is no duplication. So that means that this is something that maybe is desirable for mission critical systems. So for example, if you are sending some amount of money to some place, you don't want your account to be deducted 2 times, but it will be processed only once. So this is where you need to use exactly one semantic in the Kafka broker to be able to enable the consumer getting the data only once. So this is just showing some applications where you can use, for example, exactly once semantics for online transactional processing, transactional systems, billing system, mission critical applications where, for example, if you upload image or video, you want it to be only processed once per consumers. At most once is the place where, for example, if we are sending a temperature or humidity report, it doesn't matter whether you receive it, you receive it or you lose it because it is sent in high frequency intervals. Maybe you can use it in this kind of scenarios. At least once, for example, so if you are tracking a user's device location, it's okay to receive duplicates of the location of the user, maybe. So this can be maybe some consistency guarantee that you can use in a device, let's say location tracking application of a user or a device. So just to give you an idea, this is Spark streaming. It is actually used also for ingestion and analytics. So you can have an input data stream. So this is for real-time analytics. You have input data stream, you put it into batches and you process it on the, they call it D streams. And then you get some processed data out of this, let's say, analysis. So you can enable SQL queries on this small data set to get some processed data out of it. So you can use it for, I don't know, for social feeds, log files generated, or some payment transactions, so that you can have this processed data from the incoming batches. So now we come to the third part, which is the data analytics part. So this is more or less the AI part, machine learning part. As you can see, it's one part of the data, one framework of the data engineering pipeline. So this is the place where you do some kind of, let's say, combined streaming batch data. So batch data means you collect your data offline and you analyze it offline in maybe probably SQL queries, you get some data. Stream processing means you get the data constantly changing and you need to, let's say, get the results immediately when the data comes or produced into your system. So you can do this batch processing, stream processing, or interactive way processing. From a data analytic perspective, it's divided into 4 categories. You can have descriptive analytics. Of course, you can search for what happened into your system. Difficulty is low, but the value they get is also low. You can also have diagnostic analytics, which means that why did this happen? So this is more or less a root cause analysis. So you diagnose the system from your data. And then the predictive analytics is, of course, a little bit difficult from diagnostics. So you are going to predict what will happen next. For example, if there is an increase in the alarms in this network monitoring system, if you can predict it, you can take preventive actions before an outage happens. But the most, let's say, difficult and the most analytics category that brings more value is prescriptive analytics. Here we are dealing with the problem question that how can we make it happen? For example, it is there is some prediction. So this is actually a recommendation, some actions to influence the outcomes. For example, if there is some alarms happening in the system, maybe you can have redundant links in the transportation. So these are some recommendations to avoid these kind of disasters in your analytics. So you can also deploy these machine learning models that you have. So you don't need to, let's say, do your own framework, but you can use existing machine learning pipelines to deploy your models, AI models, for example, MLflow, Kubeflow, have this capability to give you this platform that you can, let's say, experimentally increase the version of your model, to keep track of experiments. You can deploy it to outside world. So these are actually some of the tools that you can use. Of course, PyTorch and TensorFlow already have their own platforms, like TensorFlow Serving, TorchServe, that you can also use this in your system. So streaming, we already mentioned. So streaming is the packet that is coming, or some kind of message that's coming in various forms. It can come from sockets, it can come from file-based systems, or it can even come from a message ingestion framework like Kafka. So what are the applications? For example, if we are, let's say, sending real-time notification to users via push notification, or tracking the location of users' phones, monitoring patients' bodily functions, or let's say collecting some streaming data and creating personalized products. So these are all in the realism of stream processing engines, which actually you need to know the frameworks. So one example, so there are different frameworks, tools that you can use for stream processing. Apache Spark, Flink, and Apache Beam are some examples. This figure is showing Apache Spark. So you can do SQL queries on a streaming data, or do real-time data processing with Spark streaming opportunities. You can do machine learning on the streaming data, and also graph analytics. So these are all capabilities that brings libraries, that brings, if you have this Spark in your system, to be able to analyze this real-time data in your system. I think I will skip due to lack of time. I don't know, because these are actually showing some of the terms that you can hear in the analytics, like when is the dev event is created, the time to ingest the data, processing time. So this is the end of the results. And also you can do this kind of windowing operations. So I want to see, for example, time-driven time-driven windows or data-driven windows. So I can select my window to analyze what portion of the data flowing I need to analyze. So you can also do queries for large data. Apache Hive, Peak, and Impala enables you these capabilities. So you can analyze these, let's say, terabytes of data with this SQL-like queries to get some results from the data set that you have in a big data store. So this is just to give you an example. You can have data still sitting at rest. Maybe you can use this Hive Druid to analyze your data. If the data is motioning, if the data is streaming, you can use Spark, Kafka to analyze, process the data. And the fourth item is related to data storage. So, okay, we have analyzed the data. Then maybe it's good to put it into some storage system. So this is actually, you can do storage in 3 different systems, like relational database, MySQL, Postgres, SQL, but these are not scalable. So data sets becomes problematic if you have many table sizes. You can have data warehouses. So these are like for SQL analysis, business intelligence. So this is used for long used large data. You can also have two data movements like ETL and ELT, which I will describe next. So in the extract transform load, you can have data sources, you can transform it, and you can load it into a data warehouse. In the extract load transform, let's say, feature, you can have the data sources, you can load the data into a, I would call it data lake. And then when the application wants to get the data, you transform it according to the application's needs. So this is another paradigm, which is different than the regular data warehouse. So you do this extract first, extract and then load and transform, so that you can have many bits of data, raw data stored in your data lake. So the third part is, of course, data lake, which is more in line with this ELT framework. So it's very easy to write, store large amounts of data. So you can have NoSQL databases, new SQL databases. All these databases are distributed systems, Hadoop clusters are part of your data lake. So this is actually stores more types of data, unstructured data than relational database, and there is no scalability problem. So this is just showing you the data warehouse versus data lake difference. Of course, the difference comes from extract transform load pattern. So here in the data lake, you load the data, you don't transform it. If you want to transform, you can transform the data to a data warehouse, or your applications reporting analytics system can immediately transform the data, can be given transformed data from the data lake. So this is actually showing you what kind of data types are needed. You can use these data types for different kind of databases, structured data for relational or data warehouse, semi-structured and unstructured data. There are different databases like time series, graph databases. These are all actually part of the data lake. So you need to know what kind of data type you have and how you want to store this data in a corresponding database for further analysis. So the fifth part is data monitoring and visualization. So this is okay. Now we have collected data, we have stored it someplace, we have analyzed it. So how can we visualize it, right? So we can rely on existing frameworks. So we want to uncover, understand the relationship, discover trends, maybe some real-time analytics, business intelligence dashboards. So this is where you have these kind of frameworks. For example, Kibana is one example from Elasticsearch stack. So this is the Kibana used to visualize some data set. What it does is it comes with the Elasticsearch data store. So this is actually part of the Elasticsearch stack. So it has also Logstash. So your Logstash can connect to a Kafka store. And then some file bits can be like a data connector, connecting your data to a Kafka, and Kafka can connect to Logstash. And Logstash can transform your data set into an appropriate form of Elasticsearch. And after you put your data into this Elasticsearch search engine, it is indexed. And then what you can do is to visualize it immediately. So anything that happens in real time in the files, in the edge nodes, are automatically pushed towards this pipeline into your Kibana dashboard. And it's quite useful in this kind of business intelligence and real-time visualization. Of course, Kibana is not the only one. There is more, like Grafana, Apache Superset, Apache Druid is also, or Streamlit. I don't know whether you have heard it. It's very easy to create this web applications. You can connect your web application buttons to your data set, and you can immediately see the result, some histograms. So I would actually advise you to take a look at more in this visualization tool. So you don't need to reinvent the wheel, but the thing is to know is to know which tool set you want to use, and then it's directly you can make nice visualization of your data set. Of course, you can also do others, pipeline visualization to see the infrastructure much easily, Prometheus, and so on and so forth. So this is more or less the data visualization, but like I said, data visualization is one part of the picture. You need to know how to connect to your data first. Last but not least, we have data orchestration management. So this is also important because you need to connect these frameworks together, right? You need to know where to connect, data connect to which part. So these are actually, you don't want to do it manually, but you want to do it in an automatic manner. So this is where these orchestration frameworks are coming. So if you have APIs for complex structures, you can start computation resources, services, containers with a single API calls to reduce operational cost, complexity. You can devise these workflows. This is showing the directed acyclic graph of Airflow. So you can have multiple pipelines built, and all these hundreds of thousands of pipelines are managed, can be managed by this orchestration framework. If there is some failures, it can immediately comes to your dashboard. So you can see the pipeline's health status, and even you can change this graph on the fly in your user interface. So it's very easy to use this kind of pipelines and workflows to be able to keep track of your health of your system, right? So I am visualizing it, but some parts are not visible. So you need to go to this pipeline to keep track of which parts are not behaving right. So yeah, so this is just to show you, it's not like very easy to, you have to have different tools, visualize the data, monitor the data, load the data. So there are hundreds of thousands of tools that needs to work together, transform the data. So these orchestration frameworks enable to stitch together all these tools. For example, this is an example, Apache Airflow is used from let's say data sources to until visualization of data. You can have these multiple pipelines, and all these pipelines are managed, connected by this Apache Airflow. Maybe it can be connected to your Airbyte or DBT frameworks, which can manage this underlying, let's say, ELT or ETL pipelines. So this is more or less the big picture of the data orchestration management frameworks, which is heavily used in the industry to be able to create these hundreds of thousands of pipelines to connect your data and maybe visualize it in a dashboard. So I think this was, I don't know, so just to summarize, so we have these 6 frameworks, data connection frameworks. You connect to your data source with maybe Apache Flume, and then you ingest your data, you put it into some temporary place. Maybe you can use Kafka. In the data processing pipeline, there is different kinds of processing, query-based, search-based, processing-based. So you need to know which tools you are more familiar and which one you want to more use in this kind of processing. Data storage, you can have different kind of storage frameworks. Visualization, you can have also Kibana, Grafana, and others. And of course, last but not least, management orchestration frameworks. For example, Airflow is a good example to be able to create these pipelines on a single API click, and you can manage it directly. So this is the last slide that I always show, which is showing this. Okay, the ecosystem is very large, but if you want to dig deep into, let's say, visualization, just take a look at the frameworks available and pick the one that is more suitable for you. For example, you can also try to take a look at Google Trends and other kinds of, let's say, open source community to see which visualization platform is getting much higher in the system for example, Kibana. I tried to learn Kibana. So try to learn one tool very in advance. And then, of course, learning this tool is not enough. You need to be able to learn all these different frameworks, tools also. But I would advise to you to learn, let's say, one tool out of each of these frameworks and try to connect, for example, Kafka to Flume and Kafka to Spark and do some analytics and put it into some dashboard. So this is more or less, I think, the advice that I would give for those people who wants to analyze or visualize their data in a, let's say, more professional way and more scalable manner. So I think this was all.
Thank you. Yeah, thank you, Engin. I think time-wise is very in time. Just a quick question. I mean, all these whatever 6 columns you have a highlight, each one of them, but not the last column. So which one you do you recommend in the data management column?
Yeah, this one I didn't mark it because I didn't use it in the demonstration, but I think I use Apache Flow for this. It's mostly used in the industry as well. It's very let's say robust. Apache Flow is perfect for this kind of orchestration management pipeline creation. It's very easy also to use. I would advise you to take a look.
Very nice. Question, yeah, go ahead.
Another question, but I don't see it here, but I've seen you mentioned at some stage ML Flow, and I actually encountered this tool recently where we faced quite an important problem in the project. So that was in ENSURE-6G. In ENSURE-6G, we have a couple of work packages, and there are namely 3 work packages that produce different models. So this is what we promised. For example, in our explainability work package, we said we will create a couple of models. One to do some explanations, one to find the poison clients, one to do something. Anyway, we had like, I think 8 or 9 different models. So this was work package 3. In work package 5, we had also other models to do some telemetry, data ingestion. There were models to do other fingerprinting, different models. And then eventually we had, as always in this kind of projects, some kind of orchestration work package. So we had zero-touch security and orchestration work package. What we've promised in the proposal was that these technical modules will generate different models, and then these models will be available for this orchestrator. Right? So the orchestration can take and, for example, find the poisoned clients in the network, and they can do something about this. For example, block, or maybe they can use the model to see if there was intrusion in the network, and then they can create some rules based on this. And we went to the midterm meeting, and the reviewers, of course, asked the question that we did not want it to be asked, like, how do you actually do this? So did you create some kind of, like, how do you actually make your model available to the other work package, so to the orchestrator? And we didn't know for many months, and we were trying to create, some solution, and then eventually we just said, okay, let's use ML Flow. So what we do now, ML Flow is nothing else but storing your models in a repository, but you can also keep the versioning. When you train the model, you can keep the trained model there. You can have the models that are in production, in testing, in development, and you basically, via API, make the models available to others. So very simply now, the work package 4, which is the orchestrator, can request a full catalog of the models, and they can handpick whichever model they want, and also with the API, directly use it in their module. So that was very nice, because we were kind of missing this part, and we were trying to create it, but eventually we used out-of-the-box solution like this. So when I've seen it, I thought, well, we had a very specific use case for this. And actually, when we later, Aaron, we discussed the prototype we had to show. When we created like a picture of the prototype, how everything connects together, we also had this what's called the Global Model Repository, which is actually inherit ML flow. And this is nice. And I think for people like researchers that generate a lot of different versions of the models and somehow they want to keep track of, of that versioning, that is very nice. So I recommend that one.
Yeah, so it's in complementary because here we
it was in the table.
Yeah, exactly.
Yeah.
Not in this one.
Not in this one, but in the previous tables, it was first option.
Yeah.
One of the tables like this. It was.
No, it was in the yes. I think
yeah.
I mentioned this in the.
One of the previous tables. I don't remember which
because
one.
This is more data driven. Yeah, data engineering driven, and then the ML flows is more application towards service level.
That platform. And Kubeflow I didn't use. Engin just mentioned Airflow, which also I didn't use, but it's interesting. Seems interesting. The ML flow I definitely recommend. It saved a lot of problems for us. And now in the proposals, also I know that we also promised a lot of different models being generated and algorithms. And by the way, what ML flow also gives you is you may store the model, but you may also store the whole artifact. So like a model plus all the dependencies, whatever. For example, if you Dockerize the model with all its dependencies, libraries, whatever it needs, you can also store this in ML flow. Not just the model itself, but like the whole package. And if you want to share it with friends or within the project, that's quite.
So they can be basically just click, fetch and click and run.
It's like you can deploy the model in your production or testing environment with just single API command, and you can say which version of that model you want to deploy. That's something I've seen there that I thought is overlapping with what we actually do.
Thank you. This is actually very useful for all the people in the projects who are dealing with all the potential AI-related research, especially what's actually Engin recommended here, the tables about different stages of the data handling and also visualization. So I guess given the time, do we have any urgent questions from the online audience? Feel free to raise your hands. Otherwise, I would like to thank you, Engin, for a very insightful and very technical or data-oriented talk, because I think this is clearly something that people cannot easily get from normal university education easily in such a condensed package with all the industry experience directly infused into this talk. So thanks a lot.
Thanks a lot.